go ahead and go through weak acids and weak bases. So weak acids have incomplete dissociation. So now we have this equilibrium arrow, meaning that not all of the H plus is going to be disassociated, meaning our pH is not based entirely off the H plus. So you just have to be careful with these. So anything that is not a strong acid is considered a weak acid. Weak acids tend to be organic compounds. They often are made up of CH and O. You cannot find the pH directly. We're going to have to know the Ka and or use an ice table. Weak acids will have a Ka value, and you could look those up in your appendix. And the larger your Ka, the stronger the acid. And we can also compare with a pKa, P meaning negative log. So we can find the negative log of the Ka. So pKa will increase strength with the lower pKa. To write a Ka statement is just like what we've done with KEQs. You take your products over reactants. We do not include liquids. So it will almost always look like this. H plus times the second half of that acid divided by the initial acid. So here's a typical Ka chart. So we can look these up. You'll notice it starts with these strong acids. Strong acids are considered infinite for their Kas. And so here's a weak acid, that's HF. We could look up part of HS. All of these are just different Kas we can choose. Notice we pull one H plus off at a time. So you'll see that sometimes something has multiple Kas. And so here is the process to solve a weak acid problem. We're always going to start with writing the balanced equation. Then you will write the equilibrium expression. Use ice appropriately. You'll check your assumptions, which is percent ionization needs to be less than 5%. So to find the percent ionization, you're going to take your H plus concentration divided by the initial concentration times 100. Now this check is going to work pretty much most of the time. If it does not work, then you have to not make the assumption that we make and fully solve out the math. So we're going to try this problem, finding the pH of 0.01 molar acetic acid. Okay, so I'm going to show the work here on how I did it. So notice I write the equilibrium reaction first. So I take my weak acid. I ignored water on this. It breaks up into H plus and C2H3O2 minus. My initial concentration was 0.01, and I don't have anything of my products initially. I lose X and I gain X on both sides. So I write my Ka statement always, so notice that, and I'm going to plug in my equilibrium concentrations. My assumption here is that X is going to be so small that we can say it's 0. So I wrote that note right here. I did put everything equal to my value from the appendix, which is 1.8 times 10 to the negative 5. By making that assumption, it makes the math much, much easier. So it ends up being x squared equals 0.01 times 1.8 times 10 to the negative 5. Solve for x, and you'll find that's the same thing as H plus. So here I'm writing my H plus concentration is equal to x. Make sure you include both for full credit. And then to find the pH, you take the negative log of that H plus concentration. So then we're going to check the percent ionization. So this was my X value, the H plus that I found. This was my initial concentration given in the problem statement, and I found it's 4.24, which is less than 5. Some schools or programs, wherever you are, they might make this 3%. Sometimes it's 7%. It depends on the class that you're in. So I have this practice problem for you to try. So here we have HOCl, and you need to practice making sure you can write that equilibrium reaction. We have 0.045 molar initially. So we're going to set up our ice. We're going to lose X, gain X, 0.05 minus X, X. Write your Ka statement. And then you plug in your values. Now on an exam, I would have to give you the Ka unless you're solving for it. Okay, so I am going to make the assumption that X is going to be 0. Okay, so 0.045 times 3e negative 8. And then I'm going to take the square root of that. So I find X is equal to H plus which is equal to 3.67 times 10 to the minus 5 m. Take the negative log, and I find the pH is equal to 4.43. Okay. Polyprotic acids, they're a little bit trickier. You'll notice you can only pull one H off at a time, so they actually have multiple Kas. So this is an example using phosphoric acid. 3 H's can be pulled off, and so we have different Kas. If you're not sure what to do, when in doubt, use the first Ka. It's usually the largest one, but the key is it's the one that's 10 cubed or more larger. Most likely you're not going to be doing these for a polyprotic acid. That's more likely with the titration curve. Okay, so weak bases are going to be the same idea. So here we still have that equilibrium arrow. Now I'm changing it to say weak base plus water equals a hydrogen attached to whatever your weak base was plus OH minus. So I have an example here that I grabbed from somebody. Weak bases tend to have kind of funny names. So notice how what they did here, it's identical, but then they added the H. By adding the H, they added the plus. And then you write OH minus. You write your Kb just like we write a Ka. So weak bases tend to be amines, which tend to be made with nitrogens and hydrogens. R is just a functional group or something hanging off of your functional group, and amine is actually a functional group. They tend to have funny names, and weak bases can be conjugates from a weak acid. I would highlight this part because it's usually how you see it. So for every acid that we have, we can make that into a salt. Now this thing by itself is the acetate ion. That is now a weak base. So any weak acid will have a weak base associated with it. Now weak bases can be compared by a Kb chart or pKb values. So the smaller the pKb, the stronger the base, and the larger the Kb, the stronger the base. So here's a Kb chart with some of the funny names: amide, carbonate, ammonia, hydrazine, aniline. You'll find that Kb charts are really small because usually we base it off of a Ka table because Ka and Kb are related. So to solve a weak base problem, it's the same idea as a Ka, but make sure you use a Kb value and make sure you solve all the way to pH and not just pOH. And so one thing we find in the AP world is grading, make sure you're actually answering the question. So here's an example with ammonia, which is a weak base. So you can see NH3 plus water, making NH4 plus 1 and OH minus 1. So you might remember me saying weak bases were NH3 or this guy. It is related. So I plug in my initial concentration, and then I'm going to lose X as reactants, gain X on the products. Same idea. We're going to assume that's really small. Make sure I write my Kb statement. I have a Kb value. Solve it exactly the same way I did with a Ka. Now I have my hydroxide ion concentration. Make sure you make that uber apparent that that's what it is. Take the negative log, gives me my pOH, but the question asks for pH. Sometimes on the AP exam, I would show this basic work here. Sometimes that is worth points. There is a relationship between Ka and Kb. So Ka times Kb is equal to 1 times 10 to the negative 14. Or we can take pKa plus pKb equals 14. So this is why Kb tables are so small, because they are related. So if you know the Ka of any acid, you know the Kb for its conjugate. We just take off the H+. So I have this example problem. I have HC2H3O2. It has a Ka of 1.8 times 10 to the negative 5. What is the Kb value you would need to solve for the pH of 0.37 sodium acetate solution? So we're going to take Ka times Kb equals 1 times 10 to the negative 14. I know Ka is 1.8 times 10 to the negative 5. So if I solve for Kb, I'm going to find it to be 5.556 times 10 to the negative 10. So now let's solve this. We have a 0.37 sodium acetate solution. And often we'll ignore that sodium and just write it this way. And notice now we get that acid back. And now we have that hydroxide hanging out. That concentration was 0.37. 0, 0, lose x, gain x, gain x. 0.37 minus x, x, x. Kb equals Hc2H3O2 times OH minus all over the acetate ion. We're going to assume that is really small, and this is equal to what we had just found. So I'm going to find my OH minus. So I'm going to take that Kb times 0.37, take the square root. I find that to be 1.43 times 10 to the minus 5 molar. Then I get to log that answer. So my POH is equal to 4.84. And then 14 minus that answer. And it's 9.16 for my final pH. Okay, that's a good stopping point.